Okay, so we're kind of just picking up where we sort of left off on Monday. Nothing too stressful, but essentially we're looking at rates of change and initial value. So rates of change and initial value. Now we talked about this in the last lesson, and we called it something different. We called it the rate of constant variation. It's the same thing, though. In any case, the point is when we're looking at an equation, or if we're looking at a table of values, we're trying to see if there's a rate of change. We're trying to see if there's a rate of change. That's what we're really interested in. And we're also looking at this thing called initial value. These are our two things we're always trying to identify. Okay? These two things right there. So these are our two critical things to identify in an equation. Okay, or a table of values. In this case, we're going to look at a table of values. All right, so if we look at this, so if we're looking at an initial relationship and we have a starting value and or a fixed value in that relationship, we did this with a taxi cab in the last example we did on Monday, and we did this with a gym membership as well. So it didn't really depend on the number of visits one made, so there was already a cost to it. So if we look at the initial value, we can always find it in our graph as well. So we have to think about this basically as an x and a y, like on a graph, an x and y, right? If we were looking at this on a graph, so we have our y there and our x there. So essentially, we want to know if where it's going through. We described this on Monday as either direct variation or partial variation. So direct variation, if you recall, it went through this point, right? That's a critical point. That's our origin point. So there's 0, 0. That's it right there. Okay, so if we look at this and we look at our table of values, do we see a 0, 0 in the table of values? We do. We have a 0 here and a 0 there. So we actually see that this point is on the graph at 0, 0. And in this example, this is the cost in dollars to park at Niagara Falls parking lot. So with no time, you pay no cost, all right? So what is the initial value? Well, the initial value is 0, right? So essentially, we're looking for what y is equal to when x equals 0. That is what we're trying to find. That's how we find the initial value. All right, so is it direct or partial variation? It is direct because it goes through 0, 0. If you hear a baby in the background, that's what I was talking about. You don't have enough soundproofing in this house. Trust me, he's having a great time. Okay. You can also find the initial value from a graph. So we can look at this graph, and we look at the cost. So we have our cost right there, right? And we have our other mass m in kilograms. There we go. All right, so what's the initial value? Well, the initial value is right there, right? Because it's where it's hitting through there, and we know that this is 0. So y is equal to 0. So the initial value is 0. Is this direct or partial variation? Well, we can tell it's going through 0, 0. So again, it is a direct. So if it goes through 0, 0, it's direct. And our initial value is 0. Okay. Now let's look at this one. So again, we're trying to figure out when x is equal to 0, right? So in this case here, when x equals 0, y equals 5. So what's the initial value? 5. So is this direct or partial? This one's easy. It's partial. Right? Because it has an initial value that is not 0. So essentially, if the initial value is not 0, I'm going to say that does not equal 0. Right? That the equal sign with the line through it means does not equal. All right. Can you guys actually hear my son screaming in the background? Just out of curiosity.
A little bit.
Yeah.
Okay. All right. Well, that's the way this lesson's going to go. This is the school you have now, is that you have a baby crying in the background. Okay. He's really upset. Okay, so rate of change. Again, so we talked about this as the constant of variation. It's the same thing as the rate of change. So they're kind of interchangeable. But the rate of change kind of makes more sense to people who actually speak English. All right, so in any case, it tells us the output, so the dependent variable, and it changes as the input is changed. So it's whatever thing that actually, like the number of miles traveled, might affect your fuel economy kind of thing. In this case here, our time is going to be or our cost is going to be affected by time. All right, so let's look at this, and we're going to calculate the rate of change. So we do this by calculating first differences. So I kind of showed you this last time. First differences is basically going like this. All right, maybe we'll make it a bit bigger. I don't want to screw it up too much. Erase. All right, we're having issues here. Okay. Well, it actually did erase. How about that? It only took half an hour. Okay, let's try this again. So essentially, first differences is we're looking at the difference between these things here. Right? So the first differences is the difference between those two values. So essentially, when I'm looking at it, and I'm seeing, I take my bottom number and I subtract my top number. So 150 minus 0 is 150. Now, we could do it for every single one of these. And we'd have, for example, we'd have 3 minus 150. And this one is 450 minus 3. And here we have 6 minus 450. And here we have 750 minus 6. And we'll notice that we have a common amount here. Right? And it's the same thing. We're going to do the same thing on the other side. We're going to check the differences between these two, these two, and these two. And we could do the same thing. So we go 0.5 minus 0. And here we have 1 minus 0.5. 1.5 minus 1. 2 minus 1.5. 2.5 minus 2. And so we're noticing that we have these are constant no matter what on either side. All right, so this amount is the same no matter what, as long as we look at a grouping like this, then we can compare those differences. So to calculate the rate of change, we compare the difference between the first differences on either side. So in this case here, we could compare this one with that one there, because these all match up, right? And we do it in basically foursomes. So we could do like these ones there. Either way, I'll do both examples. So for the rate of change, I can take my change in my y, like so my change in my dependent variable divided by the change in independent variable. All right, so what that looks like in this case here, I'd have rate of change is equal to 1.5 divided by 0.5, and I got 3. So I've now calculated my rate of change, because up here this is my dependent and this is my independent. Or x, and this one's y. All right, so the rate of change is easier to see because we're doing it per unit. So you'll notice that if you look in this graph, it changed by 1.5 for every half. Basically 3, where we're getting here, the value of 3 is for every 1. So it changes by $3 for every 1 hour, essentially. So we're getting a rate of basically $3 per 1 hour. That's what this means. All right, so that's going to be the cost for parking there. Now, it could change, though. You don't necessarily always give it in the increments. Like the hours, we were given in half hours. Here we're given an independent variable in kilometers, in single units, right? So 1, 2, 3, 5. Now, we're going to notice that there's a 3, 5 there. We're going to get to that in a second here. So we have different costs on the table. So we could actually compare the top two, and we're also going to compare the bottom two. All right. So if we did this, we're going to do our first differences. So I have 7.5 subtracted by 5 is equal to 250. And over here I have 1 minus 0 equals 1. Now if we look over here, we're going to do our differences again. So here I have 5 minus 3 equals 2. And here I have 1750 minus 1250 is equal to 5. Okay, so let's do both here. I'll do my green side first for a second here. So if I did my rate of change, and it's equal to the change in y over x, so this, like this. The little triangle means change in. All right, so my change in y over the change in x. So in this case here, my change in y was 5. My change in x is 2. So 5 over 2 is 250. Now let's look at if we did the top example as well. So if we did the top example, same thing. So my rate of change is equal to, and I had 250, and I can divide it by 1. And any number divided by 1 is just going to be the number on top. So 250. So that's my dollars per kilometer. So if you look at it, it doesn't matter whether you took the top or the bottom. It just matters that you do kind of a combined foursome. It has to be like this. All right? So you're comparing the difference in y compared to the difference in x. That's all we're doing. So either the change or the difference. So the change in y over change in x. All right, so we could do that by looking at a graph as well. So if you look at this graph here, right? So let's look at it for a second. And we're going to look at our graph, and we're going to compare by doing a triangle. We're going to like this here. All right, so what we're going to do is we're going to count the value that we have from top to bottom. So here, right here, we have a y value of 10. Actually, I'm going to even write down the coordinates here. So it's 5, 10. And here I have coordinates of 2 and 4. So this change from in height here, that was 10, and we're subtracting 4. So we know that the change is 6, right? The change in y. Now we could do the same thing for the change in x. So if we look at the change in x, we can see that we got up to 5, and we subtract down 2, and we got 3. All right, and I'm going to label these to make sure that it's clear what each one is. So this is my change in x, and this is my change in y. All right, so if we look at that, and we can see that the rate of change is equal to the change in y over the change in x. So we have 6 divided by 3, which is 2. And so it's 2 hours per course is the units. Basically what we have there. So if we use the graph to explain the relationship represents direct or partial variation, well, we can tell that it's going to go through 0, 0. So we know that it's direct. And we could tell what the rate of change is, so 2 hours per course. All right, let's look at another example here, and then I'll leave the last page just for you guys. Okay, so we have a linear relationship between the number of papers Ms. Festa marks and the number of candies she eats. After marking her 5th paper, she has eaten 20 candies. All right, so we have, let's make a table of values. This is going to be the easiest way to do it. So I have number of papers and I have number of candies, right? So in this case here, we have the 5th paper. She's eaten 20 candies. After 11th paper, she's eaten 38 candies. All right, does this represent a direct or partial variation? So we could figure this out by figuring out the rate of change, and we could subtract that from the whatever the 5 papers. So we'd want to know how many candies she's eaten before she's marked any papers, basically. So we can figure that out. Let's start off by doing the rate of change here. So we need to figure out which one is the independent variable and which one is the dependent variable. So does the number of papers depend on the number of candies that she's eaten, or does the number of candies depend on the number of papers? Well, in this case here, the relationship between the number of papers she marks and the number of candies she eats. I'm going to assume that I would reward myself for doing every paper. So I would say the number of candies is dependent on the number of papers. So these are my, this was going to be my dependent. So my y, and I'm going to make this my x because it'll be my independent. All right, so if that's the case, and I could do my first differences here, right, I would have 38 subtracted by 20, so 18, And here I have 11 subtracted by 5 is equal to 6. So I could say that my rate of change is equal to the change in y over the change in x. So I have 18 divided by 6, which gives me 3 candies per paper. All right, so if she had eaten 5 papers, if she had marked 5 papers, and that should be 3 candies per paper, right? That means she should have only eaten 15 candies. So in this case here, there are 5 candies left over, right? So if my rate of change is 3 candies per paper, so if it was a direct variation, so she starts at 0, she should have eaten 15 after 5 papers. But she didn't, because she likes candy too much. All right? So she obviously started eating candy before she started marking the papers. Okay. Last one here. I actually want you to solve this one on your own. So I want you to do this one, and you're going to obviously compare the slope, or calculate which one is the steepest, and you're going to have to compare the height to the width. All right? So that's pretty much it, really. The rest is going to be for you. I'd like you to do the last couple questions on your own. I'm going to put up a quiz probably either later today or tomorrow, and it's just going to be really simple on initial value, rate of change, partial variation, that kind of thing. So it should be pretty easy. Are there any questions about anything I've put up there so far?
Nope.
No? Pretty simple, straightforward? All right, let's stop it right there then. And